To this evening's webinar. We're talking about numerical methods this evening, essentially looking at how the calculator can be of assistance when students are trying to learn this topic, but also how to approach it during an exam scenario. Just a little bit about myself to start with. My name's Simon. I'm Casio's principal trainer, and excuse me, I do the training for teachers to improve the use of the handset and also creating resources so that they become more effective. I've been doing this for about 10 years now, 5 years with Casio. Before that, I was teaching, so I was using this handset in almost every single lesson, teaching A-level maths and further maths, so students would see how useful the handset could be. Okay, now because I was using the handset in almost every single lesson, what I normally do is reset the handset to begin with. So if you've attended previous sessions of ours, you may know how to do that, but I'm just going to quickly do that on the emulator that you can see on the right. So I need to go to System Manager, and the shortcut from main menu for that is the letter G. I want to reset with F5. I'm going to reset the main memory with F2. I will confirm with F1, and my main memory has been reset, so I can exit and go back to the main memory. So the main menu. Okay, so you can follow along on your own handset if you like, or you can just sit and watch. Okay, you will get a link to a recording of this session later on, though, so you can watch this at your leisure, so you don't necessarily need to make any notes either. Okay, so who are Casio Education? Why do we do these sessions? Well, essentially, we're here to make sure that teachers become more effective at using the handset so that we can increase students' understanding. Okay, we do offer training sessions, both departmental and for individual teachers. We have the emulators available, as you can see. We do support for students where we have webinars for those as well. So there are some revision webinars coming up soon for those, both A-level, further maths and GCSE. And we have loan sets available for the handsets and obviously the deep dives that we're doing this evening. And soon we will be launching an online CPD session where you can have a go at training yourself. Okay, but this evening we are looking at numerical methods. So this is part of the series of deep dives that we've been offering. This is the last one this term. Numerical methods. So benefits of graphing calculator. So it is for learning, not just for exams. So it is a very good teaching tool. Okay, you can experiment with different concepts. Students can switch their approaches quite easily. They can even have a go at, investigating on their own. And if they are doing their own investigations, they can decide whether, it's worth pursuing, will it lead to a fruitful outcome. So it is quite a useful tool. Now, when we are dealing with numerical methods, what we have is we've got some potentially tricky concepts to get our heads around. So students may have a problem with these, decimal search, fixed point iteration, Newton graphs, and they can be a little bit tricky, especially if they are, say, a bit weak when it comes to using calculus, differentiating functions, perhaps. Sometimes it's difficult to visualize what is actually happening with the problem. If you are doing an iteration, if you get a value of the function, then that's the next value of x and what happens then. Or if you are dealing with tangents, what is the process that's actually happening? And of course, like I said, if you are differentiating, how do we use tangents? How do we get the equations of those? So there are some tricky areas for students. I should say that if you do have any questions, please ask them in the background in Q&A, and I will try to get round to them at the end of the session. To begin with, I'm going to keep things fairly simple. Going to go over solving some different equations, showing you various skills that may be of use. I'm not necessarily going to regard this as a proper skill session. Press this, press this, press that. Like I say, the video will be you will get a link to the video later on, so you can watch this at your own pace. But to begin with, if we have this cubic, okay, using the calculator to approach this and help students, what we could do is we could use the equation solver that the handset has. So that's shortcut A, and then we can choose solver and then enter the equation. So it's x cubed. Notice that when you get a power more than 2, you always have to scroll to the right to enter more of the expression. We're subtracting x and subtracting 2. We do need to make it equal to 0. A ballpark figure to start with, we can start with 0. And if we choose solve, we get a value 1.5213 and so on. Okay. Using equation solver, that's useful, but it has told us that if we start with a particular ballpark value, we get a single root. We don't know if there is more than one root. So what we could do is we could actually use solve n instead. So that's in run matrix. To access solve n, use the option key. We can enter our function as we have before. So x cubed, scroll to the right, subtract x, subtract 2. I don't actually need to set it equal to 0. If you omit that, it just assumes it is. We get a warning, which we close, and we get a single value. So again, this is a more powerful feature, solve n is. However, sometimes it may miss roots because it is a numerical method. So we've got the same value. But why not a graph as well? In graph mode, we can enter our cubic yet again using our x theta t key. We're going to subtract x and subtract 2. Confirm, draw, and then you can see our function. It clearly only has one root as a cubic. We can then analyze using gsolve, and it gives us the value that we've seen before. So at this point, excuse me, we can confirm that there is only a single root that we are looking for this particular function. Okay, so if we were to use a numerical method to apply this, sorry, before we move on, I should mention that actually, because we have sketched the function, you can actually, instead of inputting the function itself as a cubic, you can just use graph notation. And this is a really useful shortcut, especially in exams. It avoids all sorts of input error. So I can just solve n, and I can say, when is my function y1 equal to 0? To access that, you have to use the vars key and graph. So then you say, okay, my function y1, when is it equal to 0? Like I mentioned before, you don't actually have to set it equal to 0. You get the warning and it calculates again. So if you have sketched the function before, you can do all sorts of operations on it just by using the graph notation instead of actually entering, in this case, the polynomial. Like I said, avoids potential input error. Unfortunately, these methods, they've not actually given students any idea upon how to evaluate. Okay, it's just giving them the answer. While students do like that, there is no method and there's no reassurance that whatever method they would apply is the correct one at this point. Just going through the numerical methods that students may need to know about. The first one we're going to have a look at is change of sign. So we're starting with the easier one for students to get their heads around. So what we're going to do is actually have a look at this in graph mode. Sorry, not graph mode, table mode, which is carried over from graph mode. So table mode is shortcut number 7. And you will see that the function is carried over from graph mode. Okay. We do need to think about the domain that we are looking at. So what we're actually going to do is look at the domain lower bound 1, upper bound 2, because we have a root in that range. Okay, so to do that, we need to choose set. Default, it goes from 1 to 5, so 1 is okay. If we change the upper one to 2, we don't particularly want to go up in integers, so let's go up in tenths instead. Doesn't have to be tenths, but it will make sense if it is. We can then investigate the value using table. And what you have there is a very nice way of evaluating functions, as you would expect using table mode. We can then scroll through and see that there is in fact a change of sign between 1.5 and 1.6. So what we have there is we have evidence that something is happening to the function between 1.5 and 1.6. There may be a root, there may be multiple roots. But we know that, below 1.5, that the function is negative, and above 1.6, it is positive at this time. So we can confirm that. You've got options to either plot the points or a continuous function. You can see that if you graph at x equals 1, it is negative. At x equals 2, it is positive, and it is actually crossing the axis between those values. Okay, so then we can take this method slightly further. We can ask about what sort of domains that we should be using at this point. And starting at 1.5 and 1.6, we can go back to set and change our bounds. So 1.5 to 1.6. We won't go up in tenths, but we'll go up in hundredths this time. You could ask students why hundredths. If we exit and then go back to the table, we can now reevaluate and we can see that between 1.52 and 1.53, there is a change of sign. So we could graph that again, and you can see we've still got the intersection with the x-axis being highlighted. Okay. So between 1.52 and 1.53, we can then start refining our search, and we keep going. 1.52, 1.53, and going up in thousandths this time. Table again. And we confirm that between 1.521 and 1.522, we have a change of sign. And we can keep on going until we get the degree of accuracy that we are interested in. But then that is a discussion saying how far would you go with your students until you have a definite value that you can say, is it 3 sig figs, 5 sig figs, 4 decimal places, and so on. And you could keep going, for example. So you could use bounds to 4 decimal places, 1.5213, 1.5214. The value of the intersection with the x-axis is between there somewhere. So then you can come up with a particular value with an error adjustment at the end. Okay, so that is a very nice way to discuss with your students, whilst you may not necessarily get a particular value, at least you have some error bounds that you can use. So you can keep going until a certain degree of accuracy is achieved. Okay, so a very nice use of table mode. However, sometimes decimal search can fail. And students do need to be aware of that. So what we have here is a slightly different cubic. I'm going to enter that into my table mode. So let's just edit that a little bit. So let's subtract 4.2 x squared and add 5.76 and subtract 2.56. Okay, so you enter your new function. Then the questions would be, what sort of domains are we going to use? You could sketch it to determine what is going on. If you do that, you would realize that, 0 to 5 might be useful. So we can set lower bound of 0, 5 to begin with, going up in integers. So this is the initial search. And what happens is that when you evaluate your table, at x equals 0, you get a negative value of f of x. At x equals 1, you get 0. So x equals 1 is a particular root. And x equals 2, you get a positive value. So it does look as if potentially the function is an increasing function between 0 and 2. However, if you graph, now this is a very rough graph because we are only going up in integers. You can see that it is negative below x equals 1, is positive above x equals 2. It's not particularly clear what's going on between 1 and 2. However, if you actually graph the function, again, in graph mode, you can see the function's carried forward. And if I choose graph, you can see there does appear to be a little bit of an up and down in the middle of our cubic. If we analyze it with gsolve, we get our x equals 1, which is confirmed by the table. But if you think there could also be roots between 0 and 1 or between 1 and 2, well, it is in fact confirmed that there is a root at x equals 1.6. Okay, now that is actually a repeated root, and using the decimal search, it has missed that. Okay, now that's one of the problems with using decimal search. It may not find the roots, especially if it's a repeated root or a root that is between two integers. In this case, or multiple roots between integers, shall we say. So unless you can actually sketch the function as well, in which case, which we have here, and analyzed it, you may miss those roots. So not an ideal method. Most of the time it is okay, but unfortunately it can miss them sometimes, and students need to appreciate that. And what you can do is, let's just do a zoom. There you go. If I do it again, there you go. So I've zoomed and just panned to the right a little bit. Might as well zoom in again. You can, in fact, demonstrate to your students that, yes, there is a root at 1, and it has got a positive gradient. It's got a maximum, which we can find. We've got a maximum at 1.2, and it has also got a minimum at 1.6. Okay, so it does increase and then decreases between the integers of 1 and 2. Okay, so that's a nice demonstration of how the method has failed, even though you can still demonstrate that there are roots there graphically. Okay. If we move on to the next method, which is fixed point iteration, this is quite a nice method. Students may be familiar with this method from GCSE, perhaps, using an iterative process. We are now going to have a go at solving this polynomial, this quintic. So what we can do is we can actually graph it. So let's just overwrite our existing function subtract 3x, and then add 1. Always a good idea to sketch the function to begin with so you know that what you are dealing with. Let's go back to the initial scale settings, and we get our function. Okay. We can analyze it, finding the roots. We can label those roots. You can see the fixed points on the graph. So what we have there is we've got 3 solutions, negative 1.38, what is it, 0.334 and 1.214. Okay, so using the iterative method, what you have to do is rearrange your functions so that you have x equals g of x. So you take f of x equals 0, rearrange it into x equals g of x. That will then give you the essential iterative relationship. So in this case, we've gone for x equals a fraction, so x to the 5 plus 1 all over 3. So those intersections should give us the same values as our quintic equal to 0. So what we can say is, let's have a go at finding our central root. So notice that the integer bounds are 0 and 1. So we can either start at 0 or start at 1, see what happens. Let's go to run matrix. If I just get rid of what we had previously. So I'm going to start at 0. So let's use 0 and enter that. So that is now my answer. Okay. So to do the iterative calculations, I use the fraction template, and then I'm going to use the answer raised to the power of 5, add 1, all over 3. Okay, so what's going to happen there is it's going to substitute the value of 0 into that, so I should end up with a third. And then I can keep repeating because it's now going to use the answer of a third into my iterative formula. 244 over 729. Keep going. We then start to get a decimal, very close to the root that it found graphically, 0.33473. And you can keep going to get even more accurate if you like. Okay. But again, it is a discussion about how accurate you would want this to be. Okay, as to how many iterations that you'll perform. But quite a useful method. In Run Matrix, students will be familiar with that. So at some point, you can make the decision to go to 4 decimal places maybe, or even 3 significant figures. Okay, but again, students need to be aware that this method, this numerical method, can also fail. It is not faultless. What happens if you wanted to find the upper root? So the upper root we can see is between integers 1 and 2. So the value 1.214. If you choose a particular starting value, so that's either going to be 1 or 2. If we start with 1, we don't have to enter this again. We can just scroll up and use the replay feature. If I enter 1, it will then perform the iterations again. And just to show you, it does begin with 2/3, obviously, and then keeps going. But what you will notice is that it actually converges to the middle root. So in fact, it has failed. Okay, it hasn't found the root that you actually wanted. And that's partly because the bounds for the middle root are also 0 and 1. Okay, but what if we were to use the starting value of 2? So if we use 2 and perform the operations again, what happens is that, let's just scroll up on the handset, it starts off with the second value, So let's say x0 is 2, so x1 is 11, x3 then 53,000. You can see that actually what is happening is that the iterative process is diverging. Okay, it's not converging to any particular route, and so again it has failed. Um, and this then prompts the question, well, why is it failing? What is the method for it failing? But is there another possible way that we could find the upper route? Will it always fail when doing fixed point iteration? Well, there is another way that you can approach this. Instead of having the fraction with the x to the 5 add 1 all over 3, you could in fact take the fifth root. So I'm just going to delete all of that and start again. So let's say that I start with a value of 2, because this failed with my fractional rearrangement, but maybe with my fifth root, it will work this time. I do need to use the answer and not x. So this is 3 times the answer, and I subtract 1. Okay. You can see that, this is actually getting closer to the upper root. If I do it again, it gets even closer. And if you keep on going, it does in fact converge towards the upper root. Okay. But notice you do need to do this actually quite a few times until the calculator is not necessarily finding more accurate values. Okay, so this is actually quite a slow process. And then you've got the question for your students, why is it particularly slow? Well, we can investigate that further. But first, here is an alternative way of approaching this. So instead of requiring students to enter it manually, the iterative formula, and then keep pressing execute, we have the recursion app, and this actually does the hard work for you. So that's shortcut 8 from the main menu. And there's different types of recursion that you can enter. We're going to stick with an plus 1. So what's the next value? I'm going to keep the fifth root because we know that does work. We've just used it. So that's 3 times an subtract 1. Okay. But with this app, as you do with the table app, you have to tell it what settings you want to use. So let's choose set. Here we can start with various values. So let's start with, shall we say, A0 at 0. Let's go all the way up to 10. So I will do 10 calculations. I need to tell it what A0 is to start with. I'm going to use 1. Now we know that the upper bound of 2 works, but remember when we used the fractional method with 1, it found the central root. Okay, well, what happens when we use a starting point of 1? Will it find the central root or will it find the upper root? So this is just an investigation tool. So what we can do is start at 1, and just so I can sketch it later on, I'm also going to tell it I'm starting at 1. Okay, the string value. If we exit and then choose table, we get our iterative values, but it has populated the table automatically. I don't need to keep pressing execute. You can scroll down and you can see that by the time you get to, say, the fifth value, 1.2142, 1.2145, 46, 46 and a bit more, and 464. So you can make the decision at that point that, the value is 1.2146. Okay. So quite nice for doing the work for you. You've got the choice again to sketch. You can do the web graph. And what this means is that it will graphically represent what is actually happening. So here you have your rearrangement, which is the fifth root and the line y equals x. When you press execute, it places the first value at x equals 1. If you keep pressing execute, it moves it up to the iterative formula value, which is 1.1. Then it moves it to y equals x. So what we're getting here is a staircase diagram. Okay. Depending upon the function you use, you could also get the cobweb. Okay. So now we're on y equals x. So the x and y values are the same. We do another iteration. It gives us a different value of y. Execute again, gives us y equals x. And again, and again, and again. Okay. So if you change the view windows, you can actually zoom right into that and see what the staircase is looking like and see that it's converging to a particular value. Okay. So there are some screenshots. You can, of course, use the other graphing facilities there. You can either graph the iterative points or you can do the graph where it joins the points, and you can see that it is actually converging very quickly to a particular value. So you've got a fairly flat line going on there, which means that it reaches a certain degree of accuracy very quickly and then just varies ever so slightly. In this case, I think it was 5 decimal places that were changing. Okay. But it may be worth investigating the failure of the fixed point iteration method. So again, if we go to our graphical method, instead of having our original function, let's sketch the g of x. Okay, so our fifth root. So that's 3x subtract 1. If we also sketch the line y equals x, now students may not realize this, but the reason that the potentially fixed point iteration is failing, it's not converging to a particular point, is linked to the derivative of g of x. So what we can do is we can do shift and menu and actually turn our derivative on. Okay, now this is particularly useful in graph mode, but also in table mode. We can exit from that, and then when we draw, we get our g of x, and we get our y equals x, as we've just seen in the recursion app, but this time we can actually trace some points. So what happens is, let's trace a point, and what happens at x equals 1, we just enter the value, and what we have here on our blue graph, which is our g of x rearrangement, the fifth root, we are told that y equals 1.14, but we also have the value of dy dx given, which in this case is less than 1. And that's the criteria for failure, that the g dash of x needs to be less than 1. You can see that if you then kept going with x equals 1.14, you would then still maintain a value that is less than 1 for dy dx. If we chose the value of 2, I think, there you go, which is the other bound for finding the upper root, you can see that we've still got a dy dx that is less than 1. Okay, so that is why if you take your xy value and then move it over to the xx, so y equals x line, and then keep doing the iteration, you can see that it will converge in this case. Okay, so there's a nice link there for students to make the understanding slightly better that the reason that it's working is because of the derivative values. If it was greater than 1, if you think about it, it would be steeper than the line y equals x. And it is more likely that when you go from your f of x value to the line y equals x, it would then diverge away from your function. Doesn't always happen that, but most of the time that is the reason that it will fail. So that would help their understanding a little bit, okay? Our final method for approaching numerical methods is Newton-Raphson. I particularly like this one. It does build on all sorts of learning beforehand, how to calculate a gradient manually, differentiating functions, and then inserting values and doing some calculations. Now, doing all of that manually can be a bit tricky. So the calculator is quite useful at helping students here. So here we have a cubic. It's slightly different. So let's exit. Let's get rid of that one. And then enter our new function. So x cubed, we're going to add 3x squared, subtract 2x, and then subtract 5. Okay. We can draw. I'm going to zoom out just a little bit so we get the whole function in there. And then when we analyze to find our roots, we can see the first one's negative 3.12. The last one, 1.33. If we go to the central one, negative 1.201. Okay, so we can confirm we're looking for 3 roots here, and we've got the integer regions. So upper root, say, between 1 and 2. Middle root between negative 2 and negative 1. Lower root between negative 4 and negative 3. The iterative process, once you have gone through the reasoning for this, obviously you can evaluate the gradient of a function at any point. So that's why evaluating dy dx is quite useful. Okay. It is linked to, the value of x, the value of f of x, and then you rearrange that. Essentially delta y over delta x. You rearrange it to get the iterative formula where you have got the derivative of your function at a point as the denominator of a fraction. Okay. If we are interested in looking for the upper root, which is between 1 and 2, again, you can approach this using the iterative method. If I get rid of all of those, let's get rid of all that. There you go. I can say, okay, my starting point is 1, so let's turn that into the answer. And then I'm going to start off with the answer and subtract a fraction. Now I need to enter my polynomial in this case. So that's starting with the answer raised to the power 3. I'm going to add 3 lots of the answer squared and subtract 2 lots of the answer and then subtract 5. So that's my f of x where I'm substituting the value of, in this case, 1 into it. And the denominator is the derivative. Now, students would actually have to differentiate their function at this point. It is a polynomial, so not too tricky. So that is 3 times the answer squared, add 6 times the answer, and subtract 2. Oops, what about there? There you go. Let's get that right. There you go. Cool. 3 answer squared, add 6 answer, subtract 2. Okay. So when you do the calculation, you get 10 over 7. You can keep going. So that's the second one. That's the third one. That's the fourth one. Okay, so it does converge very quickly to an answer that 1.330. If you kept going, you could decide whether it's going to be 1.3300 or not. So let's just keep going. Oh, you can in fact confirm that 00584 is as far as you get. Okay. But to make life a little bit easier for students, you can use graph notation. So if you have sketched it to begin with, What we can do is let's get rid of everything again. So I can start with 1 or I could start with 2. So let's start with 1 because we know that that works. Let's use the answer and subtract my fraction. Now, this is particularly useful because it does avoid any input error. So if you have graphed it correctly in graph mode, that's the important thing, obviously, you can use y1 as your function and then do y1 of the answer. So that's not y1 multiplied by the answer, that's y1 of the answer. To get to y1, we will use vars and graph. And this is now the function y, it's not the letter y. So the function y1 of my answer. Okay. And if students are not sure how to particularly differentiate, what they can do is use the differential template, and that is in option. So here's the differential template. So we're going to differentiate my function y1 again. You could, if you wanted to, put your polynomial in there, but it's easier to use y1. So again, that's vars. So that's the differential of y1 at the point answer. Okay. And then you can evaluate that. And it will keep going until you find the same values. Okay. So that's a neat little trick. Or hint, should we say, that would avoid any sort of input error. It just helps students out a little bit. Okay, it helps them to understand what's going on. So sometimes you get functions that can be a bit awkward to differentiate. So at least they know that they can get these particular values and evaluate them. Okay. Next thing, if we stick with the same polynomial, again, you can go back to recursion. So this is quite nice. Recursion is very useful, especially if you're going to do sequences in series. You can get sequence terms quite nice. Let's delete our previous functions, keep it in the blue an plus 1. So let's start off with an and then subtract a fraction. I can use an cubed, add 3an squared, subtract 2 lots of an and subtract 5. And then for my denominator, I do actually have to do the differentiation here. So this is 3an squared, add 6an, and then subtract 2. Okay. Then, as before, you need to make sure that the recursion settings are what you want. So it's with set. Let's do it 10 times. And let's start at 1. Okay. If you do that, you get the table. And as you scroll down, let's go over there, you can see that you do it once, 1.42, 1.33, 1.33, and it converges very quickly by the time you get to the fourth one. Okay, so quite useful there. Very much worth showing your students recursion. It's particularly useful in numerical methods. And again, you can represent it graphically using the web graph. That's not quite what I was looking for. Oh, that's because the scales are a bit out. There you go. Let's go to initial. There you go. Go back to web graph. Okay. So what we have there is we've got our recursion graph. We've got the line y equals x going on there as well. We've told it that we want to start at 1. So when we press execute, it starts at 1. Execute again, it goes to our function, gives us the first iterative value 1.42 that we got in the table. Execute again, it moves over to the line y equals x. So you can see that what we have is the start of possibly a staircase or even a cobweb. Okay, and if we keep going, it goes down and across. So this is in fact a cobweb. And if you do change the view window settings, you can zoom right into that to see it being formed. Okay, so again, helping students to understand what is actually going on. And again, we can exit, and you can see that very quickly when we sketch the recursion values, you can even analyze them if you want. We trace. So it starts off with 1, goes to 1.42, 1.33, 1.3300. Okay, so by the time you get to the fourth iterative value, you can see it's no longer changing. So nice and accurate for you. Okay, so helping your students out that way is quite useful. We can now have a look at a slightly different cubic. Here we have x cubed subtract x subtract 2 equals 0. If we analyze this graphically, so let's just edit the function we've got there. So this was the first function we had with our change of sign, remember? If we analyze that graphically, what we've got there is you can clearly see it's only got one root again. If we find that root, it's 1.5213. Notice we've still got the derivative turned on, so that is displayed as well. But the link between Newton-Raphson and tangents is described in the method, so what is actually happening. So why not have a go at demonstrating this with the handset so you can quite easily draw tangents. That's in Sketch. It's placed at the center of the screen, but if I know that my root is between 1 and 2, if I have a look at my lower bound to begin with, so just x equals 1, it places the tangent at x equals 1. It's a little bit messy, so what I'm actually going to do is I'm going to redraw and then just pan a little bit. So I'm going to move the graph up and to the right a little bit, just so that we can see things. So let's sketch the tangent of 1 again. There you go. So you can clearly see that dy dx is now given. So at the value of x equals 1, my function has a value of y equals -2. And a derivative value, dy dx equals 2. Now, the tangent, we can see crosses the x-axis, and the method requires you to find out the root of the tangent, where it is crossing the x-axis. That is your next value of x, and then that starts the process off. So what is the equation of the tangent? Well, quite easily to get, just press execute again. Okay. If you press execute again, you get the Cartesian equation of the tangent, so y equals 2x subtract 4. Now, notice that students could have evaluated this manually. They've got enough information. They've got the x value, they've got the y value, and the gradient. So they've got enough there for y equals mx plus c, but the calculator will give you the equation of the tangent, y equals 2x subtract 4. So if we want to find out the root of the tangent, what we will do is we will sketch 2x subtract 4. Okay. If we draw again, there is our tangent at x equals 1. To find out where it is crossing the x-axis, we can find its root. Now, you can only analyze one function at a time. We've drawn 2, so I need to scroll down so my linear function's flashing and select that. And we are told that the intersection with the x-axis is x equals 2. There we have that. Now, that is our next value of x. I mean, it's straightforward. It is 2. So we could just then say, okay, what is the equation of the tangent at x equals 2 to my function? However, if this wasn't such a straightforward value, what you can do is you can export that value to run matrix. Let's get rid of all of that. And you can say, okay, my last value of x that was calculated, I'm going to store that as a variable value. In this case, I'm just storing it as A. Okay. So if this was an unpleasant decimal or something, you have stored that value. And then if you go back to graph mode and draw, what you can do is you can say, okay, I want to sketch a tangent, but where do I want to sketch my tangent? I want to sketch it at this stored value. So I can just enter the value A, and that will give me my tangent. Even though it's not visible on the screen at the moment, because it's within the range of X values on your horizontal scale, it will plot that for you. And you can see that at X equals 2, I get a dy dx equals 11. So again, we've got enough information there to calculate the equation of the tangent, and then plot that again, and then find its intersections. Okay, to do that, quite simply, I can press execute and I get 11x subtract 18. Okay, so very easy to get the equations of the tangents and use them in your calculations. And then what you would do, you can see that the intersection of this tangent is a lot closer to the root of my function. So it does appear that the Newton-Raphson method is converging to a value that will correspond to the root. Okay, so a nice demonstration of the method that is actually being used when using Newton-Raphson. Okay, so students should get a better understanding of what they're actually trying to achieve, especially if they've only ever used the iterative method before. Okay. Last thing we can have a look at is, obviously they are making links to previous learning when using Newton-Raphson, such as, rearrangement, differentiation of functions, substitution of values, okay? Unfortunately, calculations they're a bit long, a bit tedious. Using the calculator does, of course, highlight how beneficial it is either doing the iteration in run matrix or using the recursion mode. Okay, so nice, fast, efficient use of the handset can be very useful for your students. Last thing we can have a look at is slightly different function. So we've got a cubic. Let's get rid of that. So subtracting 3x and subtracting 1. I'm going to get rid of this. If I draw it, notice we've got a cubic. We have 3 roots required, so one between -2 and -1, one between -1 and 0, and one between 1 and 2. We can confirm those values by analyzing. So there are our 3 roots. So for example, a central root -0.34. Unfortunately, if you are thinking about looking for the central root between -1 and 0, if you were going to start, shall we say, sketching a tangent at -1, and this, it very much highlights the problem. If you are looking for a root that is either where you've got the boundary values either at a stationary point or very close to a stationary point, you can clearly see that in this case the tangent is not going to intersect the x-axis, and so there is no conversion. If it wasn't exactly at a stationary point, it may, and you can see this with perhaps different functions, it would possibly converge to a different root, and so essentially failing in finding the root that you're looking for. Okay, so that's a nice demonstration of potential failure. Okay, you can also If you are sketching tangents to functions and students can have a go at finding their own functions, you can ask questions such as, why does the iteration take so long? I mean, we had a function where the iteration, it converged very quickly by the fourth go, but we also saw with fixed point iteration, there are functions that it can take 10, 12 iterations before it converges to sufficient accuracy. And why do things fail? So not just Newton-Raphson, but fixed point iteration. Why are they actually failing? Is it linked to the value of dy dx? Is it linked to the intersections of the tangents with the x-axis, and how is that affected by dy dx? So again, enabling students to increase their understanding, hopefully.